Hi, welcome back to Missing Chemistry. This is electron configuration of rhenium, Re. Okay, rhenium is element number 75 on the periodic table, so the atomic number is 75. Okay, there we go. The atomic mass number, of course, is 186. So since it's atomic number 75, we have 75 protons. Since it's electrically neutral, we have 75 electrons. And now the neutron count is going to be 186 minus 75, and that's just going to be 111. All right, now remember that the s suborbit can hold 2 electrons, the p suborbit can hold 6 electrons, the d suborbit can hold 10 electrons, and the f suborbit can hold 14 electrons. We're going to use the off-ball principle, which says we fill the lower shells first before we fill the upper shells, and we're going to use the diagonal rule. We put an X right here at the start, at the top of the diagonal rule. We're going to follow these orange-like arrows all the way down until we run out of electrons. How many electrons is that going to be? 75 to be exact. Okay, so now let's go ahead and get started. So we got 1s2. So that's easy. Slide down this slide. 2s2. Slide down this slide. 2p6. 3s2. Pretty easy, I'd say. 3p6. 4s2. See how simple this is? 3d10. Yep. 4p6. I mean, this is amazing. 5s2. So we're just sliding down the slide. 4d10. 5p6. 6s2. 4f14. Alright. And last but not least, 5d5. Alright. So let's go ahead and do this. Now, orbital notation, which involves Hund's rule, says you have to put an up arrow in every suborbit before you put the down arrow, right? Okay. So what you're going to do is you're going to go ahead, watch this, up and then down. There you go. Up and then down. Classic, 2px, 2py, 2pz. 1, 2, 3. Each suborbit has an up arrow. Now we do the down arrows. 4, 5, 6, and that's Hund's rule at its best right there. Up and down. And now we're just going to go ahead and fill these in. See how that works? Pretty darn amazing. And then 4px, 4py, 4pz, working just great. 5s up and down. And then we're just going to do these. Gotta love it. Up arrows, then we have the down arrows. So easy this is. It's pretty amazing. And then we started down arrows. And then we have 5 of these. 2, 3, 4, and 5. All right, our next type of configuration is called noble gas notation. And we have to find the nearest noble gas to Re. Now you might say, oh, radon's at the end of that particular row. We can't use radon because radon hasn't occurred yet, right? So you have to use the one before, which was xenon. All right. And then, of course, xenon's configuration ends in 5p6. See that? So you just put a xenon right there, and that just cuts all the stuff out. Now, most people, in my opinion, this is the correct method. You're going to label it in numeric order. Even though it looks not in numeric order in the electron configuration, you're supposed to do that when you do the noble gas notation. Some teachers most teachers like that. this way I'm doing it right here. And most professionals do that. But there are some people who argue that they like this method better. Just depending upon who you have, I'd say do whatever they tell you to do, but actually this is the more correct method, guys. All right, Polyexclusionary Principle states that no two elements can have the same set of quantum numbers. All right, so although Rhenium looks like it's in the 6th period, it's not, because remember that it's n minus 1, so you would go 6 minus 1 would give us 5, because it's a d block element, right? So the principal quantum number is 5. The angular momentum number, of course, is 2, because it's in a d block. And we're starting the whole count over again, it looks like. No, we're not. It's going to be the last 2 right there. So we're going to put a 2 right there. And this last arrow is going up. You see that? So that's going to be 1/2 positive. Well, that's it for this lesson. You guys be snarly, and we'll see you back here at Musin Chemistry.